Hello, hello. All right. So today we're going to read the PyTorch documentation. Honestly, it's not the documentation. It's the what do you call it? Learn section, like tutorials. Yeah, that's what I was looking for. So we're just going to read this thing. Nothing more. Right. So let's begin. So this is the PyTorch 2.x section. So introducing PyTorch 2.0. Uh-huh. But before that, I need a Google Colab. This guy, and I want to put you somewhere like this. Right. All right. Before all that, let me ensure the stream is fine. All good. Right. Over the last few years, we have innovated and iterated from PyTorch 1.0 to the most recent PyTorch 1.13 and moved to newly formed PyTorch Foundation, part of the Linux Foundation. Okay, so PyTorch is part of Linux now. I know that. PyTorch's biggest strength beyond our amazing community is that we continue as a first-class Python integrator, imperative style. Imperative style? Imperative style. That is a statement that changes a program's state, way of expressing commands, instructions. Sentence that expresses a command or request, such as come here. Okay. What is imperative style? Developer specifies step. Okay, step by step. Oh, okay. That okay. Unlike what is the other thing? What is the operator? What is the opposite? What is the opposite of declarative style? Okay, which is probably like SQL, right? Okay, got it. Simplicity of API and options. PyTorch 2.0 offers the same eager mode development and user experience while fundamentally changing and supercharging how PyTorch rotates at the compiler level under the hood. We are able to provide faster performance and support for dynamic shapes and distributed. Okay, faster and more Pythonic as dynamic as ever. Okay, so we announced Start Compile, a feature that pushes PyTorch performance to new heights and starts at the part of PyTorch from C++ back to Python and starts the move for parts of PyTorch from C++ back to Python. Oh, we believe this is a substantial new direction for PyTorch. Hence, we call it 2.0. Start compile is a few fully additive and optional feature, and hence 2.0 is 100% backward compatible by definition. Nice. Underpinning task to compile are new technologies. Task Dynamo, IIT AutoCAD, PrimTorch, and Task Injection. I have not heard about any of these, which is so cool. Task Dynamo captures PyTorch programs safely using Python frame evaluation hooks, and it's a significant innovation that was a result of 5 years of R&D. Okay. AOT AutoCAD overall PyTorch AutoCAD engine with tracing outward for generating ahead of time backward traces. PrimTorch can but canonicalize canonicalize approximately 2000 plus PyTorch operated down to class set of 250. Okay. Replanning compiler generate fast. Okay. I want to say this is nothing I should probably know, right? Probably all of them work in the backend. Wait, oh, these are the thing which makes star compile possible, isn't it? They are not other things. Okay, that's cool. To validate this technology, we use a diverse set of 163 open source models across various machine learning domains. We build the benchmark carefully to include tasks such as blah 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 blah. Okay. We don't modify these open source models except and torsional compile. Then we measure speed up. Okay. Across 163 open 90 torsional compile works 93% of time and runs 43% faster in training on NVIDIA A100 GPU. At floor 30%, it runs 21% faster on average, and AMP precision, it runs 51% faster. Yeah, it's on desktop class such as 3090. We measure that speedups are lower than on server class GPU such as A100. Really. As of today, our default backend Torch Inductor supports CPU and NVIDIA Volta and Ampere GPUs. It does not yet support other GPUs. Testimonials. Motivation. User experience. We introduce a simple function torch.compile that wraps a model and returns a compile. It does not return a compiled model, does it? What? What? Yeah, sure, right? I want to connect you and then control F9, I guess. Yeah. What? Yeah, what happened here? Okay, I don't need to then. Okay, compile. Okay, yeah. It is returning none. Model.compile. Oh, what is it called? pytorch. Optimize model equal to torch.compile of model. Okay. What am I doing? Model.compile. Okay. Okay, model.compile is probably a different thing, question mark. Torch.compile of model. Okay. Oh, okay. Bye bye. All right, all right. I mean, I get that. Yeah, the point is made. It's faster, probably, arguably. So I was using model.compile. It's torch.compile of model. Okay, cool. There's a few presets that tune the compile model in different ways. Okay. You might be running a small model that is slow because of framework overhead, or you might be running a large model that barely fits into memory. Depending on your need, you might want to use different model. Oh, defaults optimized for large models, low compile time, and no extra memory usage. API are fine. Okay. Optimizes for large models, low compile time, and no extra memory. Fastest model takes a very long time, max or dot one. Reduce overhead optimizes to reduce the framework overhead and uses some extra memory. Okay. Hooks. Module and tensor hooks don't fully work on the model, but they will be eventually work as we finish development. Okay. Serialization, inference, and exporting. Dynamo export. Okay. 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 Cool. Now we start go to get started and that's the installation. Uh, Introduction to pytorch YouTube series. Okay, I don't want that. Learn the basics probably. I mean, I think I don't need this too. Uh, Quick start. Creating models. Yeah, we create models, optimizing the model parameters. Yeah, we can do this. Saving the model, adding the model. Okay, yes. Then learning byters. Okay, learning byters with examples. Uh, Pop numpy tensors. Autograd tensors and autograd. In the example, you have to manually implement pass forward and backward pass open neural network. Oh, they do that here. That's cool. The AutoCAD package in Python provides exactly this functionality. When using AutoCAD photo of the forward pass of your network will define a computational graph. Nodes in the graph will be tensors, and edges will be functions that produce output. This, one, this sounds complicated, but it's pretty simple in practice. Each tensor represents a node in a computational graph. Each tensor represents, okay. If x is a tensor that records grad equals true, then x dot grad is another tensor holding the gradient of x with respect to some scalar values. We use pytorch tensors and autograd to implement fitting chain wave. Okay. Computation graph and autograds are very powerful. However, for large neural network, raw autograd can be a bit too low. When building neural network, we frequently think of arranging the computation into layers, some of which have learnable parameters, which can be optimized during training. In PyTorch, the NN package serves the same purpose. It defines a set of modules which are roughly equivalent to neural network layers. A module receives input tensor and computes output tensor, but may also hold internal states such as tensor and any general, I don't know. Start from minus 1.14 and send it minus 1.16. Just on optimum. Custom NN models. Cool. Weight sharing. As an example, dynamic graphs and weight sharing, we implement a very strange model. A third fifth order polynomial that on each forward pass chooses a random number between 3 and 5 and uses that many orders using same weights multiple times to compute fourth and fifth order. For this model, we can normally use Python flow, but we can implement weight sharing by simply reusing same parameter multiple times. When defining, okay, we define A to A, B, C, D. Next, we give message RB back. All right. Construct our loss function and an optimizer. Train this strange model with SGD stuff. So you use momentum. Okay, sure. SGD momentum. Okay. Oh, that works. I mean, okay. Yeah. Oh, it's fine, right? Mm-hmm. Oh, Jimmy Hogwarts. Okay. We recommend running this tutorial as a notebook, not as a script. Okay. Pytorch provide an elegant design. Pytorch.n and pytorch.optim, then dataset and data loader. Help you create and train neural networks. You have to fully utilize their powers and customize them for a problem. You need to really understand exactly what you're doing. To develop this understanding, first train a basic. Okay, I mean, I know that. Okay, that's fine. NLP from scratch. No, thank you. All right. So that's it with tutorials, I think. I mean, that's with learning the basics, I think. No, not really. We have our session here. We'll be fine tuning mask RCNN on. Okay. Are we going to do that now? Oh yeah, we are. That's fun. That is fun. Now we're talking. Uh, okay, we'll go through all these things. Okay, I think today we'll go through all these things, and then tomorrow we can go for the tutorials. I think. What is tutorials? Okay, I mean this is not helpful. What is it? What is recipes? We will look for that. Okay, in this, I mean best practice obviously. Hyperparameter tuning tutorial. Okay, that looks fun. Map. Uh, okay. How to memory by fusing optimized step into a backward password? What is that? I don't want to know that. Wait, what? Where to go? Oh, okay. Only target reducing gradient memory. And as a side effect, also optimize for intermediate memory. Thus, the more sizable memory taken up by the gradient, the more tantamount the memory reduction. Model and optimizer. I don't really understand. I don't know, man. We'll probably okay. Let's leave that. Let's go CUDA. I kind of want to learn CUDA. Maybe not. Let's learn interpretability. That's fun. Oh, TensorBoard. I kind of want to learn TensorBoard. Okay, my bad. Yeah, I want to see this thing work. Yeah, we will run this. Okay, we can do this. I should do this. So, so what are the things I want to do? I mean, I'll figure that tomorrow. Okay, Python recipes. Okay, defining a neural network. Oh, that's fun. Basics. Interpretability. Model interpreter using CAPTM. Okay. TensorBoard. Okay. Quantization. Okay. Both of these are fun. Model optimization. Real-time inference on Raspberry Pi 4. How to use a PyTorch profiler to benchmark a module's performance. Okay. Recommend. I've never made a recommendation model ever. Yeah, I should, right? Yeah, I genuinely should. Reinforcement learning. I also have never done this. Yo, I want to do this, man. Oh, this is so cool. I also want to learn this. What is TaskRec? PyTorch domain library built to provide a common sparsity in parallelism primitives and for large scale recommended games. I know. Okay, we will look all of that tomorrow. maybe the day after tomorrow also. Okay, today we focus on translation, right? Not translation. Oh, object detection fine tuning tutorial. Okay. So what is mark arsenal? I don't want to download it, but here we are. Okay. Oh, gaming he. I know him. Facebook research. I know that. Okay. B present a conceptually simple, flexible, and general framework for object instance segmentation. Oh, is this the predecessor for SAM? Is masked RCNN related to SAM? No, I don't think he's the right person to ask. This is fine. Yes, Mars, Arsenal, and SAM are related since they are both instant segmentation models, but with key differences. 27 and 2023. Two-stage detection first identifies regions of interest, then generates mask. Requires training on specific object classes, output both bounding boxes and segmentation masks. Prompt-based approach they can segment any object. Zero shot capability, not needed training needed for new objects. More flexible input method, points, box, text. More flexible input methods. Built-in transformer rather than CNN backbone. Okay. Okay. So let's start on Coco dataset. Okay. So you given an image, you mask the image. You probably have limited what do you call it? The objects which you can do it. For example, humans maybe, and bottles and things like that. Cars definitely. Cool. So okay, is there running collab obviously? Okay. I don't need any tips. I'll just run it. Let's go control offline. 2 minute sessions. Okay, sure. Connect. I can't have two runtimes. I thought I could. Anyways, control offline. Okay. Get this data set. We'll look into what this data set is. Okay. It contains 170 images with 345 instances of pedestrians. Okay. 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 Runtimer. No such file directory. Okay. Now what do I do? Guess I needed this thing after all. Yeah, anyways. So read the image. Fine, we'll leave it. Defining the data set. Okay. For in Windows, okay. Writing a custom data set. So we have the data set. We read image. Okay, this is how it looks. with translation we make the custom data set. We have get item length and you need one more like index probably. Okay, so you probably don't have to index here. That's fine with me. Defining your model. So this is the model. We do a projection. Deep convolution network. Role. I don't know what role is. Pooling layers, fully connected layers for each role. Mask RCNN and an extra branch into faster RCNN, which also predicts segmentation mask. For instance, uh, I'm not familiar with the architecture, but okay, it is a CNN based architecture. Fine tuning from a pre-trained model. Okay, so import torch vision. Faster RCNN predictor. So model we have torch vision dot models that did what? No. Okay, we can load using one line. Honestly, it is not even torch hub. You are loading a model from torch vision dot models. Okay. Hmm. Why is there both torch vision dot models and torch hub? Serve different purposes. Torch vision dot models specifically for computer vision models. I mean, who cares? General purpose repository for any domain. Data integrated into PyTorch ecosystem limited to models implemented in torch vision. Okay. Support community. Oh, it is a subset. So Torch Vision, so Torch Hub has everything. Okay, then I'll probably always use Torch Vision. No, I misspoke. Number of classes. One class is person plus background. Okay, modifying to add a different back one. Okay, I don't know what you're doing, but okay. Object detection and instance documentation for twin food and data set. Okay, putting everything together. Okay, we define model, data set. Okay, what do you mean engine? Hmm. Sure, yes. Okay, anyways, transfer learning for computation tutors. Okay, you can read more about transfer learning in this notes. In practice, very few people train entire AI from scratch with random initializations because it is relatively rare to have a dataset of sufficient size. Instead, it is common to pre-train convolutional net on a large dataset and then use the convolutional net as either as an initialization or fixed feature factor for the task of interest. Yeah. This is generally what is called what a fine tuning, and this is generally what is called transfer learning. Though both is kind of what, mm, mixed. Fine tuning and as a feature extractor. Yeah, that's what I was saying. BSc lessons. Okay. Food and then dot benchmark recorded true. What do we do by? Load the data obviously. Visualize images, enchant ends, training the model, since equal to time to time. Oh, here a temporary directory to save training checkpoints. Best model path for epoch. Okay, we choose this face. Each epoch has both faces. Iterate on the data. Okay. Then optimizer.0 guard. We take the input. Optimizer.0 guard. We predict the output. We do what is that? Then we do loss calculation. But what is this? What is this data set then? Okay. Visualizing model predictions. General function to display pictures. Predictions. Fine tuning convolution. Convenant. Loading RusNet 18. Hmm. Inference on custom images. Okay. That's fair. Adversarial example generation. Building software, you can appreciate how effective some machine learning models are. Research is constantly pushing machine learning models to be faster, more accurate, and more efficient. However, an often overlooked aspect of designing a training model is the security and robustness, especially in the face of adversity who wish to fool the model. This tutorial will raise your awareness to security vulnerabilities. Threat model for context. There are many categories of adversarial attack, each with different goals and assumptions. However, in general, over overarching goal is to add the least amount of perturbation to input data to cause desired misclassification. There are several kinds of assumptions that the attacker starts with, which are white box and black box. A white box assumes the attacker has full knowledge and access to the model, including blah blah blah. A black box attacker assumes the attacker only has access to the input and output of the model and know nothing about the underlying architecture. Fast gradient sign attack. One of the first and most popular adversarial attacks to date is referred to as the fast gradient sign attack and described by Goodfellow. Okay. The attack is remarkably powerful and intuitive. The, it is designed to attack neural networks by leveraging the way they learn gradients. It's simple rather than working to minimize the loss by adjusting the weight based on the backpropagated errors. That the idea is simple. Rather than working to minimize the loss by adjusting the weight based on backpropagated error gradients, the attacker adjusts the input data to maximize the loss based on the same backpropagated gradients. In other words, the attacker uses gradient of the loss with respect to input data and adjusts the input data to maximize the loss. So into this you add 0.007 of this, which gives this. But for human eyes, literally the same. Is there any difference? I don't feel any difference, man. Hmm. Okay, 57% panda, random thing given with basically 100% confidence. Cool. Okay, so how do we stop that? There are three input for this tutorial. Epsilons. This of epsilon value for the it is important to keep 0 in the list because it represents the model's performance on the original test. Also, intuitively, we would expect larger than epsilon. They noticeable the perturbations, but the more effective it. Okay. Oh, model under attack. Okay. Okay, so we basically make a model from scratch and model it where pre-trained model. What is pre-trained model? What pre-trained model? Okay, some pre-trained model. Yes. FGM attack. Cursor versus epsilon. As epsilon increases, the accuracy or decreases very drastically. Simple adversarial examples. Remember the idea of no free lunch. Yeah, no model is the best at any situation. In this case, as epsilon increases, the accuracy decreases, but the perception becomes more easily perceptible. In reality, there's a trade-off between accuracy, degeneration, and perceptibility that an attacker must consider. Here, it shows some of the successful adversary. Okay, blah blah blah. DC again. This will give an introduction to DC again. Okay. I don't think I want to learn again now. Spatial transformer network. You will learn how to augment your network using visual attention mechanism called spatial transformer networks. Okay. Behavior transformer model. What is the EIT? Okay. Generally, transformers is a model that require more data set, right? Like, are you sure about this? Oh, DEIT is data efficient image transformer. Can complete. Okay, okay, okay. Transaction time pandas request. You get the data set, you load the model. Okay. Azure model is this. Script and context model, script and context optimized model, date model. Okay. Audio backend reinforcement learning, deploying pytorch models in production. Introduction to Onyx. Open Neural Network Exchange is an open standard format for representing machine learning models. The expert model can be consumed by the many runtime supports in Onyx, including Microsoft's Onyx runtime. Currently, there are two flavors of two Onyx export API, but this tutorial we will focus on. Okay. Okay. Deploying my other code is later. Okay. Simple web server. Following is a simple web server taken from Flask documentation. Okay. I must learn this. I must learn the basics of Flask. Translation import models. Mm, with open of this one, image by mean I'm not getting much of these. This is actually deploying a model, right? Man, I think I have to learn what like basic Flash or Flask before approaching this. This introduction to task script, okay? Tutorial is an introduction to task scripts, that an intermediate representation of pytorch model that can then be run in high performance environments. Okay, so this is a model cell actually. I run the cell, something a little more interesting. We made task are linear. Sure, we redefine a model, but this time we have linear attribute and we invoke several linear in the forward function. This is exactly what's happening here. I mean, what exactly is happening here? Examine the flexibility. Wait, oh, it's a GIF. Okay. Hmm. So what are you doing? Hmm. I will look into it later. Relying inference on, okay. Profiling PyTorch. PyTorch includes profiler API that is useful to identify the time and memory cost of using various PyTorch operation in your code. Oh, okay. Profile the forward pass. Okay. Okay. Nice. Most operating are forward of 10. Uh-huh. I don't see that, but okay. No problem with this. We can say two consumes. Okay, we'll look into it, man. This is cool. And this will let us know what to do to make the model faster, right? Holistic trace analysis. Okay, holistic trace analysis. Okay, blah blah blah. Analyzer equal trace analyzer to path to the folder. Time spent equal to analyzer that get temporal breakdown. Okay. Front-end APIs. Extending by task. Model optimizations. Profiling your model. Oh, this is the same thing, huh? Okay. PyTorch profiler with a tensor bot. Oh, these are the same things, huh? All right. You have to run this out. Yeah, I think I'll continue tomorrow. Yeah, thank you for watching. I think I'm going to end this now. Yeah.